Okay, so we will cover the operation, device physics and operation of JFETs. And then after that, I want to start BJTs. All right. So let's get to JFETs. All right, junction FET structure, JFET structure. There are a few things going on, okay, in here. We spoke about how the JFET is created from either a solid substrate of N-type or P-type material. The type of the semiconductor that is used to create the structure is also the type of the channel. So if you create a JFET from N-type material, it is an N-channel JFET. And if it's a P-type material, then it's a P-channel JFET. What we do is we implant or diffuse P-type material into an N-type material. And so we have two identical P-type material or P-type structures on either side of our N-type substrate. And because of that, there is a channel that is in the middle that is of N-type. Majority carriers in N-type is electrons, minority carriers are holes. In a P-channel JFET is the exact opposite. It's a P-type material, an implanted or diffused N-type material on either side. So we have majority carriers of holes and a P-type channel. Okay. So that's where we stopped. We have the source, drain, and the gate, which is symmetrical. Let's look at what happens if we apply voltage at the gate and the source. Internally, the two P-type regions are connected together. Okay, so these two P-type regions are connected together internally, and they form one single terminal of the gate. Okay, so it's not independent. Our explanation focuses on N-type material or an N-channel JFET, but the explanation applies equally to a P-channel JFET. Okay, P-channel JFET. All right, so here we are not applying any bias between the gate and the source. The drain is grounded, nothing is, VDS is 0 volts. We are not applying anything between the drain and the source. We are simply looking at the effects of biasing voltage on the width of the channel. Okay. So when VGS is equal to 0, this is the biasing state when it comes from the factory, right? No external energy source. So channel width is basically designed from the factory. When you pick it up off the shelf, that's what it is. Now we apply VGS and we bias the gate negatively to the source. So we are reverse biasing the gate and the we are reverse biasing the gate with respect to the drain and source. So we are reverse biasing the gate with respect to the source. So VGS is negative for a N-type material. We are applying positive at the source and negative at the gate. And it's measured with reference to VGS. So in N-channel JFETs, we would say VGS is negative. So if you did the JFET lab, then if you recall, that we applied a negative voltage. So when you apply a negative voltage, what happens? Well, just from its creation, we have a depletion region here, and we have a depletion region here. So there are two depletion regions. And this is simply a result of the fabrication of the device. We have two depletion regions, and we have a channel between the two depletion regions. Well, if VGS goes negative, what happens? When you apply a negative voltage to a depletion region, it starts to expand, right? The charge carriers, the holes on the P side and the electrons on the N side are pulled away from the junction So the depletion region starts expanding. The depletion region width increases. That's what's happening here. The depletion region width increases, but the channel width decreases. Right? You have two depletion regions expanding or encroaching on the channel from both sides. So the W here refers to the width of the channel. Okay, it refers to the width of the channel. Okay, so depletion regions are increasing on both sides, width of the channel decreases. You keep increasing the VGS voltage until both depletion regions merge together. When both depletion regions merge together, the channel no longer exists. And we say that the channel is pinched off. We say that the channel is pinched off. And that value of VGS that is required to pinch off the channel or to close off the channel is known as the pinch off voltage, VP. VP. At this point, we can say the device is off. Okay, the device is completely off. It's reverse bias, yes. It's reverse bias. All right, let's take a pause. Let me know if you have any other questions. No, we are not at that point yet. This is simply like a channel does not exist. So the key point here is that when the device rolls off the factory floor, to use a vehicle analogy, that device has a channel that already exists. Okay, it does not need any application of voltage or current to create a channel. That is one of the big differences between a regular MOSFET and a JFET. Okay, a channel already exists. We need to apply a voltage to turn the device off. We need to apply a voltage to turn the channel off. Yes. So question being asked is the device bidirectional? I don't know, you tell me. It's a good observation. If it's fabricated symmetrically, then it is bidirectional, yes. So drain and source terminals could be interchangeable. That gives me an idea, probably an additional procedure for the lab. Just after everything is done, you flip the device or you flip the connections and just see if it works. Right? And that'll prove whether it's symmetrical or not. But if fabrication is symmetrical and everything else remains the same, then yes, the device is symmetrical. You can flip the drain and the source. All right, any other questions? So far so good. Everybody understands what pinch off voltage is, right? Okay. So now let's see what happens when we apply a voltage between the drain and the source. We have the channel. We have the carriers in the channel. If we apply an electric field across it, then the carriers should move in direction of the electric field, right? So let's see what happens when we apply VDS. So drain to source voltage. Drain to source voltage. So let's say VGS is equal to 0 volts. We are not applying any voltage at the gate and the source. So the channel that exists at the factory is the channel that we have. Okay, we are not closing it or reducing it by any means whatsoever. If VGS is 0, channel is wide open, and we apply an electric field between the drain and the source, what will happen? The charge carriers in there will drift in response to that applied electric field, hence field effect transistor. So when VGS is 0, we apply VDS, and carriers will drift in response to the electric field. Okay, remember the drift and diffusion currents? It's coming up soon. What is drift current? I just wrote it on the board. Carriers drift in response to an electric field. What is diffusion current? Sorry? Yes, but what was it? Diffusion current was a result of imbalances in the doping concentrations. So at the PN junction, we have the doping or charge carrier imbalance. On one side, we have a heavy concentration of electrons. On the other side of the junction, there is a low concentration of electrons. And so the electrons will diffuse through the junction in an effort to balance out the charge distribution. That was diffusion. Okay. All right. So what is happening here? When we apply VDS, current will start flowing. Electrons are attracted towards the positive. Somebody on Zoom, please send a message. Let's just kick us out. Hopefully not. Okay. So as I was saying, electrons are in there in the N channel. We are applying positive at one end, negative at the other. So electrons are attracted to the positive terminal of the battery or the external electric field. Current starts flowing. Obviously, current flows in the opposite direction. So electrons are flowing this way. No, electrons are flowing this way. Current flows this way. And that's why we have IS. Okay. Does that make sense? Yes, no? Yes, okay. All right. So now, take a few seconds and look at the biasing. Let's say VGS is 0, right? 0 volts. But you're applying positive voltage at the drain and negative at the source. What does it do to the depletion regions? Look at the. So what is the application of VDS? The drain to source voltage. We are applying a positive voltage at the drain, negative at the source. So we're applying an electric field across the channel to attract the charge carriers. So the charge carriers, which in this case are electrons, are attracted by the positive end of the source. And so current starts flowing, right? Electrons are moving in this direction. So currents IS or ID is flowing in the opposite direction. But what does it do to the depletion region? And how and why does it happen? What kind of channel do we have? N channel. And what kind of voltage are we applying at the drain? So it's a reverse bias. And because it is reverse bias, what happens to the depletion region? At that end, at the drain end, the depletion region is expanding. And that's what's shown here. So it doesn't happen at the other end, but at the drain end, where we are applying a positive voltage, you have the same effects. Depletion regions are expanding, but now they are more towards the drain end. And so it starts pinching off, well, not quite pinching off, but coming close to merging together. So the effects are not the same as what we experienced in the previous slide. Previous slide, it was VGS, where the entire structure, the entire depletion region is expanding. Here, it's only towards the drain, only at one end. If we flip the drain and source terminals, then we would see the effect on the source side, not on the drain side. But on the drain side, it is starting to merge. And when it gets close to merging, we have a similar pinch-off effect. Okay, we have a similar pinch-off effect. And one caveat to this is, of course, all of the dimensions in here are exaggerated just for effect and for explanation purposes. Okay, the dimensions are exaggerated. So a merging effect takes place. Okay. Reverse bias makes it pinch off. Well, reverse bias increases the depletion region width, and because it's increasing the depletion region width, it results in pinch off. We'd have to go back to chapter 2. But since the question is being asked, let me explain. We have a p-type material, we have an n-type material. P and n-type material enclosed together, we have a depletion region in the center. In the depletion region, there are no charge carriers or free charge carriers. In the P side, we have an excess of holes. In the N side, you have an excess of electrons. So positive charge on the P side, negative charge on the N side. If we apply reverse bias, what we are doing is we are applying a positive voltage to the N side and negative voltage to the P side. When you apply positive voltage on the N side, it attracts all the electrons. So their electrons are pulled away from the junction. On the P side, you're applying negative voltage, so it pulls away the holes from the junction. It's a depletion region, that's why it keeps on expanding. And that's why it keeps expanding. Maybe I should ask that on the final exam. Explain in words, how does a depletion region work? Well, now you know the answer. You can put on your headphones in the exam and listen to it. Yeah. All right. Kidding aside, let's come back to our discussion. So if we apply VDS, the answer is that current starts flowing, but with increasing VDS, that comes a point where the channels merge off. So if I was to plot this, I was to plot the flow of current, let's say like this. Voltage on the x-axis as always. So VDS, applied drain source voltage on the x-axis. And I have ID or IDS or IS. It's all the same. Doesn't really matter. Drain current, source current, drain source current. You can call it whatever you want. If we apply voltage why is it not doing that? Ah, there we go. That should be close to 0, but that's good enough. So with increasing VDS, we have increasing current. Linear relationship. So it behaves like a resistor. And this is something we saw in the lab. So for those of you who did perform lab 6, we saw this in the lab, right? It starts increasing linearly with increasing voltage. So voltage increases, current increases. But after a certain point, what happens? What did we see? We saw that it saturates. So what's happening inside the device? Pinching off. But if it's pinching off, how is current still flowing? it's pinched off here, how is current still flowing? Maybe they dug a tunnel through it, which I'm trying to crack a joke, but is actually what is happening. The electrons are tunneling through the barrier. So that's where the drift and the diffusion effects come into the picture. So if we go back to chapter 2, I believe, or chapter 2 or chapter 3, I can't remember which one. We spoke about how when we bring the two PN junctions together, the total current that flows in these semiconductor devices is because of drift and diffusion. Drift is the effect of charge carriers moving or drifting in response to an applied electric field. Diffusion is a response where there is an imbalance of concentration, or there's a gradient in the charge carrier concentration, meaning the charge carrier concentration is high at one end and low at the other end. And so the carriers diffuse from higher concentration to lower in an attempt to even out that concentration. So what is happening here is that, yes, the depletion regions are coming to merge together, but there's a small point, right? It's not, there's a small gap, if you will. And the electrons have already been attracted to that point, up to that point by the electric field. So now in the depletion region, again, as the name suggests, it is completely depleted of charge carriers. There are no electrons present in there. So there's an imbalance of charge carrier concentration. There's heavy concentration of electrons in the channel, and then right across in the depletion region, there are no carriers. So there is a depletion, there is a gap in the concentration. And so now the electrons are kind of diffusing through. And when they diffuse through that barrier, we have diffusion current. There is no drift current whatsoever. It results in a so-called gap. So the electrons are now diffusing through there. And once they go through there, they are now again influenced by the electric field, and they are able to acquire energy and tunnel through. So most explanations will have you say that there is a gap and the electrons are tunneling through that gap. Okay, but by many accounts, what is happening is electrons first drift, arrive at the merge point, then they diffuse into it, and once they diffuse through, they're again attracted by the electric field, and they are now going in a steady motion. And this rate remains steady because it's already pinched off. So the rate remains steady, hence we have a flat line. And so at that point, it behaves like a constant current source. So before it reaches that pinch off, it's behaving like a linear resistor. After, it's behaving like a constant current source. So two different models to explain the same device. All right, let's take a pause. There was a lot of words and a lot of talk. Let's take a pause. You think over that. Let me know if you have any questions before I write down a few other things. Yes. Well, yes and no. Current source is just any device that can supply a constant current. Sure, yeah. One of the ways we can make a constant current source. Yeah. But any of our benchtop supplies, if we run in constant current mode, that is a current source. So the only difference between a voltage source and a current source is the mode of operation. If it can supply a constant voltage, it's a voltage source. If it can supply a constant current, it's a current source. So any benchtop supplies that we have in our lab benches, they are both a voltage source as well as a current source. There's a tiny CV or a CC somewhere on the front panel. That's all it means, yeah. All right, any questions? Any other questions? Okay. All right, so For all intents and purposes, this is also a pinch off region. Okay, but do not confuse it with VP. Okay, this would be VDSP. So this point where this pinch off occurs would be VDSP. The VDS voltage required to pinch off the channel. But when it comes to JFETs and FETs in general, if you're talking about pinch off voltage VP, which is on the spec sheet, then we are referring to VGS and not VDS, right? Because VDS can have multiple levels. VGS is measured with no applied VDS. Okay. All right. So now, as we saw in the lab, if we applied a negative VGS, let's say minus 0.5, what happens to the channel? The channel shrinks. If the channel shrinks, then the total amount of current that's already flowing in the channel is going to reduce. And so even if we applied another voltage, the max that would be permitted to flow through would be lower. And we increase VGS again, far more negative. We'd obtain a third set of data. And then a fourth, and so on and so forth. So we can obtain a set of curves for every single applied VGS voltages, right? So this is VGS is equal to 0 volts. This is VGS is equal to some negative voltage. I want to say 0.5. VGS is equal to minus 1. And so on and so forth, right? Until it completely pinches off. So at the bottom, at the very bottom, we'd have no. And here I would say is VGS is equal to VP. Channel is completely cut off. No matter what VDS voltage we apply, there's no current flow. Okay, there is no current flow. VGS is equal to VP. VDS can be any value, and ID will still be 0. Okay. This current right here is the max value that is obtained, and so that's IDSS. And this region right here is the linear resistive, or also known as the triode region. Okay, triode region. What is the equation or formula for resistance? Anyone remember? Rho L or A, right? So remember I said this is the linear or the resistive of the triode region because it behaves like a linear resistor. So we can define the resistance of the channel within this triode region. And that depends on the physical characteristics of the channel. The channel itself is built like this, right? So you have the channel in the middle. And let's say approximately like this and like this. So we have the length of the channel, and then we have the width of the channel. So that's looking from the top. And if you look at it in the Z direction, this is the X and Y direction. The Z direction would be the depth of the implant. How deep did we implant into the region, right? And so we can write an equation or an expression for channel resistance. RCH. RCH is rho L over TW. Where T is the depth of the implant. How deep did our diffuse impurities go? Okay, so rho L over TW. Cross-sectional area of our device. Okay. All right, then let's look at the characteristics, device characteristics. Again, you'll be familiar from the lab. We have the output characteristics on the right. You have the input characteristics or the transfer characteristics on the left. Why does this keep doing that? There we go. So we have input characteristics, output characteristics, ID as a function of VDS, and we have the transfer characteristics, ID as a function of VGS. Okay. IDSS, of course, is the max value right here. The triode region to the left. The way we obtain the points on the left is we simply translate them on this side. That's how we obtain the transfer characteristic. The equation for the drain current ID can be given by ID is equal to IDSS. IDSS is manufacturer specified, but due to differences in doping, there is a wide range. If you'll remember, for J113, what was the range for the pinch-off voltage from the data sheet? Yes. Yep. It was, well, it was -3 though. So minus 0.5 to -3. So very large variation. But in the lab, I think the variation was some lab kits had, so some student groups had like 1.6 volts as their pinch-off voltage, and some groups had about 2.5 as their pinch-off voltage. There was no in between. But still, I mean, according to the manufacturer themselves, there's a wide range of variation. There's one more equation. I just want to talk about IDS can be obtained from parameters Kn over 2 times Vp square. Let's see if we have time to. Yeah, we don't have time to go into. Okay, I wanted to get this done. All right, let's just quickly work through this problem. That's the last one before we get to MOSFET. So we only have about 6 or 7 minutes left. What I'm going to do is I will continue on after 4 p.m. If you have to leave at 4, you can leave at 4. That's fine. I'm just going to keep recording and explaining. And so then you can watch the recorded portion later. But it should not take more than a few minutes. Okay. So for JFET biasing, meaning we are setting up the circuit, we are applying a DC voltage on the output side, and we simply have one resistor each at each of the 3 terminals. Okay. We're asked to find the Q point. Q point in this case means finding the value for VD as well as ID. Okay. So the question being asked is determine the Q point for this circuit. Okay, determine the Q point, meaning we need to find the voltage for the device and the current for the device. ID is not the diode current, it is the drain current in this case. Okay. Now, when we approach this, we have our standard equation. The standard equation is that the drain current is IDSS times 1 minus VGS or VP the whole square. Okay. IDSS is given to us. VP is also given to us. What is not given to us is the VGS that is being applied. Okay. So if we wish to find ID, that's what we need to do. Okay. So as with most analyses approach, what we do is we apply KVL on both the input as well as the output side. So we apply KVL in this case. And on the input side, I can identify 3 different voltages in the input loop. Right? You have the resistor voltage RG, you have VGS, and you have RS. So on the input side, I have VRG, I have VGS, and I have VRS, 3 voltages. I apply my KVL, I can just sum up these voltages and I can say I equate them to 0. So VRG plus VGS plus VRS is equal to 0. Okay. I can apply Ohm's law and express each one of these in terms of their currents. So I can write gate current IG times RG plus VGS plus IS times RS is equal to 0. Typically, gate currents are very, very small. So if we assume IG is equal to 0, at this point, the assumption is purely for convenience. Okay, we assume it to be 0 so that it eliminates, one quantity. So if we eliminate VRG and of course the drain current and the source current are exactly the same. So IS is equal to ID. I can rewrite this expression as VGS is simply equal to minus IS times RS is equal to minus ID times RS. Okay, minus ID times RS. So what do we do from here? We have the equation on the left, which is the standard equation for ID, the drain current, and we obtain the circuit equation by applying KVL. We can plug in this relationship into the equation for ID, right? Because ID has this VGS, and so I can take this and plug it into the equation right here. Because VGS is unknown, it's not given to us. So if there are too many unknowns, we make assumptions, we simplify it as much as possible, and then we begin solving for it. Okay, so I would say plug this into the equation for ID. Okay, and then I can write, rearranging the terms, I can write VGS is equal to IDSS times 1 minus VGS over VP the whole square times RS. Okay. Then try solving for this. VGS comes out to be 0.005 1 minus VGS over VP square times 1,000 and then keep on reducing this. VGS is equal to 5 times 5 plus VGS over 5. Oh, wait, I'm plugging in. I skipped one step. No, that's actually correct. This is minus 5 here. This may 5 plus VGS over 5 the whole square. All right, and then this gives me, I'm going to take the 1 over 5 outside, and inside I get 25 plus 10 VGS plus VGS square. Where? Oh, we had a we had a negative from above. So this entire expression had a negative there. Okay, so then my final equation comes out to be VGS square plus 15 VGS plus 25 is equal to 0. I would strongly recommend students use their own calculators to calculate. Since you already have the answer here, the roots of this come out to be VGS is equal to minus 1.91 volts or equal to minus 13.1 volt. Okay. So what do you think is the right answer? Is it 13.1 or is it 1.91? VP is given as 5. So it can't be 13.1. If it was 13.1, it would simply be pinched off. You would not have any current flowing through. And so, because VP is given as minus 5 volts, the only logical choice is that VGS would be 1.91 volt. Okay, that's the only logical choice. All right. So if VGS is 1.9, we can calculate ID from there, right? From the above equation. Right here. VGS is minus ID times RS. So 1.91 substituted in there, and we have RS value that is already given to us. So we can calculate. I'm going from here to here. Drain current is the same as the source current. Is VGS over RS. So 1.91 milliamps. In order to find, so we found 1, meaning the drain current. The other coordinate of the Q point is VDS. To find VDS, apply KVL at the output. And when you apply KVL at the output, we obtain VDD is equal to ID times RD. Actually, again, I'm skip. VDD is equal to VDS plus VRS plus VRD. And therefore, VDD is equal to ID times RD plus VDS plus IS times RS. And therefore, my actual VDS in terms of the other quantities is VDD minus the voltage drop across RD minus the voltage drop across RS. But ID and IS are the same, so I can combine them and I can find VDS as 12 minus 0.00191, 1.91 milliamps times RD plus RS. So combined value of drain and source resistance. This gives me a value VDS as equal to 6.27 volts. So, over 7 minutes over time. Apologies about that, but that's where we'll end class today. Next week, quiz on Monday. Based on the material we have done this week, I'll post another homework. Some of it's based on FETs, some of it's based on diodes. And then quiz will be based on material that we've covered this week. And we'll begin BJTs. MOSFETs, we'll look at the end of the class, probably in the last week of class. But the next few weeks is all BJTs. Okay. All right. Happy Halloween. Have a good weekend, and I will see you all on Monday. Yep. Yes. Yeah. Yes. Oh, because it's actually not positive. I skipped. Sorry, hold on here. Because VGS is minus ID times RS. So minus 1.91 equals minus, so minus signs just cancel out. Right here. VGS is minus 1.91 volts.